Ozone, ʻoʊzoʊn, or trioxygen, is an inorganic molecule with the chemical formula O3. It is a pale blue gas with a distinctively pungent smell. It is an allotrope of oxygen that is much less stable than the diatomic allotrope O2, breaking down in the lower atmosphere to normal dioxygen. Ozone is formed from dioxygen by the action of ultraviolet light and also atmospheric electrical discharges, and is present in low concentrations throughout the Earth's atmosphere. In total, ozone makes up only 0.6 ppm of the atmosphere. Ozone's odor is sharp, a reminiscent of chlorine, and detectable by many people at concentrations of as little as 10 ppb in air. Ozone's O3 formula was determined in 1865. The molecule was later proven to have a bent structure and to be diamagnetic. In standard conditions, ozone is a pale blue gas that condenses at progressively cryogenic temperatures to a dark blue liquid and finally a violet-black solid. Ozone's instability with regard to more common dioxygen is such that both concentrated gas and liquid ozone may decompose explosively. It is therefore used commercially only in low concentrations. Ozone is a powerful oxidant and has many industrial and consumer applications related to oxidation. This same high oxidizing potential, however, causes ozone to damage mucous and respiratory tissues in animals, and also tissues in plants. Above concentrations of about 100 ppb. This makes ozone a potent respiratory hazard and pollutant near ground level. However, the ozone layer is beneficial, preventing damaging ultraviolet light from reaching the Earth's surface, to the benefit of both plants and animals. Nomenclature. The trivial name ozone is the most commonly used and preferred IUPAC name. The systematic names 1-lambda-1, 3-lambda-1 trioxidane and catena-trioxygen, valid IUPAC names, are constructed according to the substitutive and additive nomenclatures, respectively. The name ozone derives from ozine, the Greek word for smell, referring to ozone's distinctive smell. In appropriate contexts, ozone can be viewed as trioxidane with 2 hydrogen atoms removed, and as such, trioxidane may be used as a context-specific systematic name, according to substitutive nomenclature. By default, these names pay no regard to the radicality of the ozone molecule. In even more specific contexts, this can also name the non-radical singlet ground state, whereas the diradical state is named trioxidanidyl. Trioxidanidyl is used, non-systematically, to refer to the substituent group. Care should be taken to avoid confusing the name of the group for the context-specific name for ozone given above. History. In 1785, the Dutch chemist Martinus van Marum was conducting experiments involving electrical sparking above water when he noticed an unusual smell, which he attributed to the electrical reactions, failing to realize that he had in fact created ozone. A half-century later, Christian Friedrich Schobein noticed the same pungent odor and recognized it as the smell often following a bolt of lightning. In 1839, he succeeded in isolating the gaseous chemical and named it ozone, from the Greek word ozine meaning to smell. For this reason, Schobein is generally credited with the discovery of ozone. The formula for ozone, O3, was not determined until 1865 by Jacques-Louis Sauret and confirmed by Schobein in 1867. For much of the second half of the 19th century and well into the 20th, ozone was considered a healthy component of the environment by naturalists and health seekers. The Beaumont, California, had as its official slogan, Beaumont, Zone of Ozone, as evidenced on postcards and Chamber of Commerce letterhead. Naturalists working outdoors often considered the higher elevations beneficial because of their ozone content. There is quite a different atmosphere at higher elevation, with enough ozone to sustain the necessary energy to work, wrote naturalist Henry Henshaw. Working in Hawaii, seaside air was considered to be healthy because of its believed ozone content, but the smell giving rise to this belief is in fact that of halogenated seaweed metabolites. In fact, even Benjamin Franklin believed that the presence of cholera was connected with the deficiency or lack of ozone in the atmosphere, a sentiment shared by the British Science Association. Physical properties. Ozone is colorless or slightly bluish gas, slightly soluble in water and much more soluble in inert nonpolar solvents such as carbon tetrachloride or fluorocarbons, where it forms a blue solution. At 161 K, it condenses to form a dark blue liquid. It is dangerous to allow this liquid to warm to its boiling point, because both concentrated gaseous ozone and liquid ozone can detonate. At temperatures below 80 K, it forms a violet-black solid. Most people can detect about 0.01 μmol per mole of ozone in air where it has a very specific sharp odor somewhat resembling chlorine bleach. Exposure of 0.1 to 1 μmol per mole produces headaches, burning eyes and irritation to the respiratory passages. Even low concentrations of ozone in air are very destructive to organic materials such as latex, plastics and animal lung tissue. Ozone is diamagnetic, which means that its electrons are all paired. In contrast, O2 is paramagnetic, containing two unpaired electrons. Structure. According to experimental evidence from microwave spectroscopy, ozone is a bent molecule with C2V symmetry. The O distances are 127.2 pm. The O angle is 116.78 degrees. The central atom is sp² hybridized with one lone pair. Ozone is a polar molecule with a dipole moment of 0.53 d. The bonding can be expressed as a resonance hybrid with a single bond on one side and double bond on the other, producing an overall bond order of 1.5 for each side. Reactions. Ozone is a powerful oxidizing agent, far stronger than O2. It is also unstable at high concentrations, decaying to ordinary diatomic oxygen. It has a varying half-life length, depending upon atmospheric conditions. In a sealed chamber with a fan that moves the gas, ozone has a half-life of approximately a day at room temperature. Some unverified claims imply that ozone can have a half-life as short as a half an hour under atmospheric conditions. 203302 This reaction proceeds more rapidly with increasing temperature and increased pressure. Deflagration of ozone can be triggered by a spark, and can occur in ozone concentrations of 10 Wt% or higher. With metals, ozone will oxidize most metals to oxides of the metals in their highest oxidation state. For example, Cu plus O3 CuO plus O2 with nitrogen and carbon compounds. Ozone also oxidizes nitric oxide to nitrogen dioxide. No plus O3 number 2 plus O2. This reaction is accompanied by chemiluminescence. The number 2 can be further oxidized. Number 2 plus O3 number 3 plus O2. The number 3 formed can react with number 2 to form N2O5. Solid nitronium perchlorate can be made from NO2, ClO2, and O3 gases. Number 2 plus ClO2 plus 2O3 number 2 ClO4 plus 2O2. Ozone does not react with ammonium salts, but it oxidizes ammonia to ammonium nitrate. 2NH3 plus 4O3 NH4NO3 plus 4O2 plus H2O. Ozone reacts with carbon to form carbon dioxide, even at room temperature. C plus 2O3 CO2 plus 2O2 with sulfur compounds. Ozone oxidizes sulfides to sulfates. For example, lead sulfide is oxidized to lead sulfate. PbS plus 4O3 PbSO4 plus 4O2 sulfuric acid can be produced from ozone, water and either elemental sulfur or sulfur dioxide. S plus H2O plus O3 H2SO4 3SO2 plus 3H2O plus O3 3H2SO4. In the gas phase, ozone reacts with hydrogen sulfide to form sulfur dioxide, H2S plus O3SO2 plus H2O in an aqueous solution. However, two competing simultaneous reactions occur, one to produce elemental sulfur, and one to produce sulfuric acid. H2S plus O3S plus O2 plus H2O3 H2S plus 4O3 3H2SO4 with alkenes and alkanes. Alkenes can be oxidatively cloven by ozone, in a process called ozonolysis, giving alcohols, aldehydes, ketones, and carboxylic acids, depending on the second step of the workup. Usually ozonolysis is carried out in a solution of dichloromethane, at a temperature of -78 oC. After a sequence of cleavage and rearrangement, an organic ozonide is formed. With reductive workup, ketones and aldehydes will be formed. With oxidative workup, carboxylic acids will be formed. Other substrates. All three atoms of ozone may also react, as in the reaction of tin chloride with hydrochloric acid and ozone. 3SnCl2 plus 6 hydrogen chloride plus O3 3SnCl4 plus 3H2O. Iodine perchlorate can be made by treating iodine dissolved in cold anhydrous perchloric acid with ozone. I2 plus 6HClO4 plus O3 2I3 plus 3H2O. Combustion. Ozone can be used for combustion reactions and combustible gases. Ozone provides higher temperatures than burning in dioxygen. The following is a reaction for the combustion of carbon subnitride, which can also cause higher temperatures. 3C4N2 plus 4O312CO plus 3N2. Ozone can react at cryogenic temperatures. At 77 K, atomic hydrogen reacts with liquid ozone to form a hydrogen superoxide radical, which dimerizes H plus O3 HO2 plus O2 HO2 H2O4. Reduction to ozonides. Reduction of ozone gives the ozonide anion, O-3. Derivatives of this anion are explosive and must be stored at cryogenic temperatures. Ozonides for all the alkali metals are known. KO3, RbO3, and CSO3 can be prepared from their respective superoxides. KO2 plus O3, KO3 plus O2. Although KO3 can be formed as above, it can also be formed from potassium hydroxide and ozone. CSO3 plus Na plus Cs plus NaO3. A solution of calcium in ammonia reacts with ozone to give to ammonium ozonide and not calcium ozonide. 3 California plus 10 NH3 plus 6O3 California 6 NH3 plus California 2 plus California 2 plus 2 NH4O3 plus 2O2 plus H2. Applications. Ozone can be used to remove iron and manganese from water, forming a precipitate which can be filtered. 2 Fe2 plus O3 plus 5H2O2 Fe3 plus O2 plus 4H plus 2Mn2 plus 2O3 plus 4H2O2 MnO2 plus 2O2 plus 4H plus. Ozone will also reduce dissolved hydrogen sulfide in water to sulfurous acid. 3O3 plus H2S 3H2SO3 plus 3O2. These three reactions are central in the use of ozone-based well water treatment. Ozone will also detoxify cyanides by converting them to cyanates. Cn- plus O3 Cn- plus O2. Ozone will also completely decompose urea. 2CO plus O3N2 plus CO2 plus 2H2O. Ozone spectroscopy. Ozone is a bent triatomic molecule with three vibrational modes: the symmetric stretch, bend and antisymmetric stretch. The symmetric stretch and bend are weak absorbers, but the antisymmetric stretch is strong and responsible for ozone being an important minor greenhouse gas. This IR band is also used to detect ambient and atmospheric ozone, although UV-based measurements are more common. The electronic spectrum of ozone is quite complex. An overview can be seen at the MPI-UV Vis Spectral Atlas of gaseous molecules of atmospheric interest. All of the bands are dissociative, meaning that the molecule falls apart to O plus O2 after absorbing a photon. The most important absorption is the Hartley band, extending from slightly above 300 nanometers down to slightly above 200 nanometers. It is this band that is responsible for absorbing UVC in the stratosphere. On the high wavelength side, the Hartley band transitions to the so-called Huygens band, which falls off rapidly till disappearing by 360 nanometers. Above 400 nanometers, extending well out into the near, are the Chappuis and Wolf bands. Their unstructured absorption bands are useful for detecting high ambient concentrations of ozone, but are so weak that they do not have much practical effect. There are additional absorption bands in the far UV, which increase slowly from 200 nanometers down to reaching a maximum at 120 nanometers.